Okay, can I have everybody's attention?
I think so.
All right, we are finally ready to get going. I wanted to introduce our speaker today. Also, I'll have a lot of people here. I want to make just a quick announcement. There's going to be a physics club meeting that's going to be held on Friday the 17th, and it's going to be held at 5:30 p.m. at Sherlock's Pub. So if anybody doesn't mind having to go there after work, that would be a good place to go. And also, you can see that or any other announcements on our Facebook page. Also, I'd like to announce our speaker tonight. Last week, we had a speaker, and he talked about Marie Curie, who was one of the greatest scientists of all time. And now we've got one of the other greater living scientists right here. This is Patricia Reiff. She's a professor at Rice University, and she's also one of the leading experts on space weather. And so this has been an exciting time the last few weeks for space weather. If you've been watching, there's been a lot of activity going on the sun and things like that. And this would be the person to talk to you about. And I met Patricia a few years ago. We were working on a proposal for a Center for Commercial Space Transportation in Houston. So I've got a chance to work with her, and I can tell you from firsthand experience that she's a brilliant woman, and that this is going to be a fascinating talk.
Thank you very much. Okay, so I made the title "The Slumbering Giant Awakes" because there for a while we were pretty scared as to whether the sun was going to come back at all, because we did have a very long dry spell of dead space weather, just like last summer. We had a pretty bad dry spell of no rain and a lot of heat. I was evacuated from my ranch 3 times, but fortunately we didn't burn. Well, yeah, just the introduction is pretty general. Most of you know this, of course. The sun is the most important star for life on Earth, and life today is almost entirely dependent on the energy from the sun, either old or new. We'd like to see a lot more real-time solar energy. Can we put on the lights? Well, what is space weather? Space weather is not tropospheric Earth weather as seen from space, and I think this is a picture that's going to be fairly familiar to you all who suffered through Hurricane Ike a few years ago. Space weather is not weather as observed on other planets, as the great red spot here. Instead, space weather is the variation in the Earth's environment as a response to changes on the sun. The sun, of course, is always there. It has a constant solar wind. It has a constant insolation, but it has dramatic events that happen on the sun that can cause dramatic changes on Earth. Well, when the energetic particles and then the plasma from the sun hits the Earth, but there are many beautiful and dangerous things that can happen. What can happen is a solar flare releases a blast of particles. There's 2 blasts of particles. One is the solar energetic particles that come at the speed of light, and then there's the slower CME particles that run into the Earth's magnetic field, store magnetic energy in the magnetic tail, and then release it explosively, causing the aurora northern lights. And what can happen if we have a sequence of space weather events like we've had lately? What can happen is the 1-2 punch can be a lot more deadly, because with the solar flare, the energetic particles come to the speed of light, but then they're gone. And it's only a day or 2 later that the plasma comes and opens up the magnetic field. Okay? By then the energetic particles are mostly gone. But if then you have a second flare that occurs while the magnetosphere is open from the first flare, that can be the problem, and that happened just last week. So we'll talk a little bit about the sun as a star, sun's energy, our magnetosphere, the aurora, and magnetic reconnection. I love this picture because it shows two plasmas in the same shot. This is comet held off with the plasma tail and the aurora seen over Boston a few years back. Well, the sun's an average kind of star, primarily hydrogen and helium. Temperature on the surface is 6,000 Kelvin, which is hot, but not like the corona. The sun has a cute green flash, and those of you who have been out to sea have seen some green flash. In fact, I saw one. I got a good picture of one when I was on an eclipse cruise last year. The energy output in the visible part of the light is quite constant in time, but it's the energy in the other parts of the spectrum that are important for space weather. And these vary with a roughly 11-year cycle. Of course, as you know, the energy is produced in a thermonuclear reaction to the core of the sun with a radiation zone and then a convection zone, where the bulk of the energy is now convected to the surface, and that convection is quite important until you get to the photosphere, where then radiation takes over. Because you have convection, then you have a stirring of the magnetic field on the surface. Well, if you look at the solar spectrum, at the top of the atmosphere, it's very nearly a black body with a peak of yellow, which is about a 6,000 Kelvin black body. But here at the very shortest wavelength, the X-rays and the ultraviolet is where the greatest changes occur at solar maximum. So the sun bubbles up, energy bubbles up in the convection cells. Each one of these convection cells is about the size of the Earth. And if this were a solar eclipse, you would see this as a prominence. That's a helium image. H-alpha looks pretty similar. And then we can actually watch these convection cells bubble. And they come up, they rise in the light ones and fall in the dark areas. Angles of that magnetic field. You can think of magnetic fields as sort of rubber bands, and if you wind them up like you do with a paper airplane, you can put a lot of energy into that magnetic field. Well, with a paper airplane, then you let it go by, letting it go. But the way the sun lets the magnetic fields go is through a process called magnetic reconnection, that you allow those magnetic field lines to reconnect with each other. And when they do, they can cause great energy output. And this reconnection occurs all the time. It doesn't just occur in flares. In fact, these are what we call micro reconnection, happens all the time on the sun, and that's how the sun actually heats the corona from the 6,000 Kelvin of the surface to millions of degrees temperature in the corona. So this very hot temperature corona is caused by this reconnection process happening on a small scale all the time. Electrons are stripped away from the atoms ionized. If you look at the surface of the sun, the ionization state is quite variable from one to completely. By the time you get to the solar wind, it's almost completely fully ionized. The old joke was the two were walking along and bumped into each other, and the person said, "Hey, you stole an atom, or you stole an electron from me." How do you know? Because I'm positive. Well, anyway, the combination of electrons and atoms acts like a fluid, and partially because it acts like a fluid, was given the name plasma. But it's the fourth state of matter, as in earth, air, water, and fire. Well, it takes a lot of heat to make a plasma. If you ionize just by collisions, then you have to have very, very energetic particles colliding to get the collision ionization. But energetic photons can also do your ionization from you, giving an ionization state which are not thermally, more heavily ionized than you would think just from the temperature of the plasma. Well, there's not a lot of plasmas you could see besides fire. And fire is not that big plasma. But the aurora borealis is one, and of course, who's seen the aurora? Oh, that's great. It's definitely one of the most spectacular things in the sky. And I've been fortunate to see it a few times, but it was scary that I'd studied the aurora for 15 years before I saw one. Well, in any case, the aurora is caused by electrons trapped in the Earth's magnetic field, hitting the upper atmosphere, causing it to glow. The highest altitude aurora is red, from a 6,300 line of oxygen. The main aurora is green from a 6,577 line of oxygen, and the blue and crimson are nitrogen lines. And so we get the different colors at different altitudes. So we can use spectroscopy from the ground to discover what the energy input is, because the more energetic electrons penetrate deeper. When you have most of the aurora that people see is green. Their eyes are very adapted to seeing green. But if there's a very, very low latitude aurora in a major storm, then it tends to be red because it's mostly low energy electrons deep in the magnetosphere. Well, the aurora has rays aligned with the magnetic field and has curtains that extend east-west that actually go all the way around the Earth. Electric charged particles are stuck on magnetic field lines because of the Lorentz force. One particle says turn left and left and left and left and left, and so he's stuck on this field line, and the particle of the other charge is going to right and right and right and right and right, and he's stuck on this field line. And so you can actually see the field lines, because if one field line has more plasma on it, it will look brighter than its neighboring field line. So auroras, you can actually see the magnetic field lines, and in the solar corona, you can actually see the field lines as well because of the electrons that are on them. Here's a video of an aurora, and again, you can sort of see the purple lower border here. The main green, the high altitude red doesn't show up real well in this movie. Here's another one that the high altitude red does show up well. This is a sequence taken from the space shuttle. So you can see the lower altitude green and the high altitude red rather well. So because the shuttle goes up to 55, it can kind of skim along the auroral zone. You don't want to cross on the north side of the aurora because the aurora really tells you the boundary between the magnetic field lines that are trapped and the magnetic field lines that extend out into space. So once you've crossed forward of the aurora, you are now on magnetic field lines that extend into space. And so another one of these solar flares, the energetic particles come, and that's when the space station can be in some risk. And that was this one that we had just a couple weeks ago was very close that they were concerned about. But it turned out they did not do any maneuvers from this latest event. But Delta Airlines did cancel a cross-pole flight. It costs money. So they're very eager to know whether these kinds of things will happen because it's much cheaper to fly from Chicago to Beijing or the pole than it is around the side. So it's always interesting to teach people about great circles. I always give my teachers a piece of string and have them actually measure the distance if you go this way versus over the top, and it's noticeable. Well, another question you can see are comet tails. Comets have two tails: a dust tail that extends away from the sun, and in the orbit of the comet. But the blue ion tail it follows the solar wind, and because the comet has a finite speed compared to the speed of the solar wind, there's an angle between the ion tail and the dust tail. And it was this angle between the ion tail and the dust tail that allowed fellow Bierman to estimate the speed of the solar wind even before we had spacecraft out there. We could tell it was 300 to 400 kilometers per second just based on the angle between the ion tail and the dust tail. But they didn't really know whether it was there all the time. All they knew it was always there when the comets were there. The most fun plasma, of course, to see is the solar corona. And it's light scattered over electrons trapped or really falling out of the sun. You'll notice there are certain magnetic field lines that you can see. These are called Helmut streamers, where the corona is bright. And then there are other regions where the magnetic field line just extends into space. This is called coronal holes, and the ones that are called polar coronal holes. Whereas the streamers near the equator are more trapped, and so the solar wind that comes from that sort of diffuses more out from space, about 300 to 400 kilometers per second velocity, whereas the speed of the solar wind out of the pole is more like 600 or 700 kilometers per second, so about twice as fast. And you can kind of think about, the garden hose. You let the water, come out of it in a stream, and stream, but once you put your thumb on it, you can make it go much harder and much faster. A solar maximum, on the other hand, the solar corona is much more symmetric. You get these helmet streamers all the way around. So you see an eclipse picture, and you see only the corona near the equator, then you know it's near a solar minimum. An eclipse is one like this, where the corona is all the way around. It's the solar maximum. The solar maximum eclipse is also a lot more fun because you get more of the prominences on the edge, and the corona itself is brighter. Well, I've been to 12 times on the center line. I lived in Ring once. This was one of my close ones in China in 2008. We had a cloud that, we moved at the last moment. And I call it dragging each sun because we had this cloud in my hand, and it was just right around the sun. But what's cool about about a solar eclipse is you get a sunset all the way around, which is really, really fascinating. Eclipses also, are just things of beauty. The diamond ring, which is the last bit of the sun right before it goes into totality, is a great thing to photograph. And this one, right near a cloud off Tahiti, gave us some beautiful rainbow effects in the clouds. Like this was from 2010, and again, closer to low solar minimum, the corona is much more concentrated in the place. Now, in case you want to go to an eclipse, there's a couple of them coming up. There's an annular eclipse coming up May 20th. Unfortunately, we won't be able to see it from Houston. We'll see the partials from Houston, but we won't be able to see the annular part. It's best, over the Pacific. It comes ashore in Northern California, near Reno, so you can go see the annular eclipse at Reno. And I'll probably be in Albuquerque, so straight over Albuquerque. And at Albuquerque, it will be an annular eclipse right before sunset. And it will still be eclipsed as it continues to set. So if you want to see a cool eclipse. Now, the difference between an annular eclipse and a total eclipse, in an annular eclipse, the apparent size of the moon is small because it's farther away, and the apparent size of the sun is a little big because we're closer to it. And so it leaves a ring of the sun left behind. So you won't be able to take off your eclipse glasses. You sometimes can see the corona through a video camera, but you don't want to look at it with your eyes. So annulars are interesting, but they're not as spectacular as a true totality. Now the cruise that I'm going to be on this fall in Australia, we are going to be close to solar maximum, so we'll have a much more symmetric and brighter eclipse. And then there's going to be a transatlantic cruise in 2013, and that's the plug if you want to join me. Well, when you get the nice thing about having eyes in space is that we can now create our own total eclipse in space anytime we want to, because the problem really isn't the corona, problem is the atmosphere, scattering light. So once we get up outside of our atmosphere, we can basically put our thumb over the sun and see it glowing. And this is the SOHO imager. This is the outer corona. So this is the size of the actual sun under there, and that's the size of the disk, and there's the arm holding the disk out. And this is one of these solar flares. And the two things you notice with the solar flare from the corona is that it appears to be a ring coming out concentric from the sun. That's called a halo CME. If the CME comes off the side, it's very beautiful and easy to see, but it's not something that's heading toward us. Well, one's interested in the ones that are heading toward us, and there appears to be a ring that's expanding from around the sun. The other thing you notice is all this snow. That snow is the energetic particles from the sun actually hitting the CCD camera that's taking these images. So whenever you see a snow like that on a rolling movie, then you know it's heading our way. And expect black line. This black line? Well, that's just the arm that's holding out the stick. It's basically, a camera that's got a stick holding a disc, and that's the stick holding the disc. Most of the time you can't see it but when there's a lot of activity, it's easier to see the stick. As I mentioned, the ultraviolet X-ray part of the sun varies tremendously with solar minimum and solar maximum. This is all the same exposure as the alpha X-ray images. This is what the sun looks like in solar minimum, and this is what it looks like in solar maximum. It's the same. It's the same brightness scale. You notice that there's a couple of features you see in X-ray. One is these hot spots, which is the active regions of the sun. The other thing are these dark lanes, these are the thermal holes. And the thermal holes are always at cold, but then they can also come down to lower latitudes. If one of these thermal holes points towards the Earth, then we get this very high-speed stream. So that's another way we can get solar activity on Earth, is from one of these high-speed streams coming along. You can have a high-speed stream activity not necessarily related to a flare. Fortunately, we can use the proxy, the F10.7 radio noise as a proxy for the energetic ultraviolet and X-ray fluxes, and what we see is a function of sunspot number, the 10 centimeter flux goes up substantially. So when I'm a ham operator, so we want to know how good the ionosphere is, because the ionosphere is nice and dense, and we could bounce off of it and possibly around the world. So ham operators are always looking at the F10.7 flux, because that says that you've got a lot of ionizing X-ray or extreme ultraviolet. Well, sunspots are relatively long-lived on the sun. They will rotate with the sun. You'll notice they generally are not exactly at the equator, but early in the solar cycle they start at high latitudes, and at later in the solar cycle it goes lower and lower altitude. This was a tremendous one that caused one of the biggest solar storms that I have personally looked at. This is called the Halloween storms. There was, a sequence of like two big storms. This one blew off, and then 3 days later, that one blew off, and they hit us in a 1-2 punch. Well, sunspots are dark because they're cool, but they're still hot. And in fact, they are regions of very, very strong magnetic fields. Part of the reasons why they have strong magnetic fields is it's a very localized convection cell. So these sunspots, if we now flip them over and look and see what they look like, you can see these deep convection cells that are stirring up the sun's outer envelope. And as these convection cells happen, then that winds up into the seed magnetic field. We see the upflow on the outer part and the downflow. And if you've got a seed magnetic field, then a straight convection of neutral plasma doesn't cause a current. But if there's a seed magnetic field, then the electron has a tendency to go one way and another way, and it creates a current which then either reinforces the magnetic field or causes it to decay. Well, once you get these tangled up magnetic fields, then the best way to release them is a flare. And there's a flare then that's letting go one of these coronal mass ejections. And a coronal mass ejection can be 100 million tons of material that leaves the sun. Of course, that one was off the edge, so it didn't come toward us. Here's another one from SPO. And you can really see these magnetic fields. You notice they go from one sunspot to the next, generally. Sometimes after a big solar flare, it'll turn into an arcade. It looks like a caterpillar almost. This one I call the trebuchet, because when it let it go this way. And you notice a lot of the material falls back down, but some of it gets ejected into space. And that's just true of a lot of things. You know, you have a distribution of energies, and some falls right back down, and some goes into space. It's the same way if we look at the volcanoes on Io. You see the material on Io coming up, most of it turns around and falls back down, but what's left is enough to power basically all the plasma you use in these magnetospheres. Similarly, we've seen now jets at Enceladus at Saturn that a few of the particles get all the energy. One of my favorite demos, which I forgot to bring, is like 4 balls on a stick and a big ball on the bottom and graduate. Have you seen this one? And you drop it, and all the energy goes to the little ball. It goes bam, 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 bam. Kids love it. Well, the sunspot cycle is just constant. It goes with approximately a 10, 11-year cycle, but all cycles are not the same. And in fact, there was an extremely long period of time in 1600 where there were almost no sunspots at all. That was called the London minimum. And in fact, here's where Galileo discovered sunspots with his telescope. If he hadn't gotten a telescope to hear them, we would have not known about sunspots for another 36 years. And the one thing that's very interesting about low sunspot numbers is they're associated with cold weather. This is a very cold time in New England. There was years without summer. There was freezing at the Thames. There's another really cold time in the early 1800s. And in fact, interestingly, in 1913, when the Titanic sunk, was a time of very, very low sunspot numbers. So in fact, the time that the Titanic was about the same sunspot situation as we've had in the last few years, about 3 years with no sunspots at all. and that gives you extremely cold weather in the northern hemisphere. And I think it actually contributed to the Titanic sinking. We have a planetarium show on the Titanic that we bring this up. We're going to be showing it again at the Museum of Natural Science. We're updating it, putting some new animations, and it's a little open, I think, March the 10th, just in time for the 100th anniversary of the Titanic sinking. So, in a sense, you could say that the Titanic sinking was the space weather event with the greatest loss of life, because there was no sunspots, so there was no aurora. Turned out that it was very cold, so the icebergs persisted down to 40 degrees north latitude. They normally don't. They normally would be melting away, just having occasional iceberg at that latitude. But because of the very low sunspot number, it was a very, very cold time. The other interesting thing about the correlation between low sunspot number and cold weather, we don't really understand how it works. Best model I've heard for how that works is that in sunspot maximum, solar wind is very, very strong, and so it keeps out the galactic cosmic ray because the entire heliosphere becomes larger. It pushes against the interstellar medium. And so the stronger the solar wind is, the farther away the heliopause is, and the harder it is for galactic cosmic rays to come in. And when the galactic cosmic rays come in, then they can create nucleation centers in their upper atmosphere to the clouds. So it's not so much that the sun doesn't put out enough radiation, there's just more clouds reflected back away. The Earth's albedo is a really critical point in the calculation of Earth's temperature. You go from an ice age to a green age if we change the albedo of the Earth. So something like this, where you have more clouds when the sun is weak, is a way to make things cooler. And finally, that's one of the reasons why global warming hasn't been as apparent in the last few years as it could have been, because we've had a minimum in the sun. So the human aspect has been doing this. The sun had a local minimum, and so we had a little plateau in our climate change. But now that the sun is coming back, I think we're going to, I predict in another year we won't have any more naysayers about global climate change when the sun comes back. This shows you the deepest, the number of spot-free days. These are the record spot-free days on history. Here's 1913 for the Titanic, 1901, here's 2008, 2009, 2007 are three of the years of the least spots. Here's 1912. As I said, the Titanic years and this recent sunspot were very comparable. Now, of course, one of the things we have is a prediction of how the sunspot size is going to look, and of course they update it periodically. It's going to change all the time. We first, if I showed you this plot 5 years ago, we would have said that the next sunspot maximum would have been 2011. Well, that didn't happen. And in fact, the sunspot minimum extended much longer, much deeper than anybody expected. But as you can see, we started to see a turnaround. Those are the monthly numbers as of September 2010. Here it is as of June 2011, and there it is as of January. So we're definitely coming back, and we may be back on track for a maximum in 2012. We really but it will be here soon. But as you can tell, the predicted maximum was going to be about 80, and we've already had a month with 90. So things are looking good. As mentioned, that when the very first sunspots of a new cycle have a tendency to occur at very high latitudes, and then as the sunspot progresses to maximum, they move to more equatorial latitudes, and that's what they call this the butterfly diagram. The brightest areas of the X-ray are these magnetic bubbles, and if they were on the edge, they would correspond to prominences. Here's a rotation of a solar minimum X-ray sun, and again, you see the active regions as bright spots in X-ray. The sun's rotation is not uniform. It rotates faster at the equator and more slowly at the poles. If we now look at different layers of the solar corona, we can see the different magnetic field signatures of the inner corona. We look at from these images from SOHO and now from SDO. We look in various ionization lines of oxygen and carbon to look at different layers of the corona. And this is the helium. So again, I see a prominence on the side. So if it's just hanging there at the prominence, if it's exploding, it's a flare. A lot of people get those things mixed up. Now, one of the cool things that we now have is a spacecraft called Stereo. And Stereo started off from Earth, but one of them went into an interior orbit, so it started going faster, and one went to an exterior orbit, so it started going slower, and they slowly have drifted ahead of Earth in its orbit around the sun. So they're in a solar orbit, but the ahead spacecraft at this point was exactly 90 degrees ahead of Earth in its orbit, and the behind was 90 degrees behind Earth in its orbit. So they could see the whole sun from the side. And the cool thing about that is then they can easily see the coronal mass ejections that are coming our way. So this is the one that's ahead. This is the one that's ahead in the orbit. So anything that's on this side, if it was going straight out on this side, it would be coming toward us. And similarly, this is the guy that's behind us in our orbit, and anything that's coming out this side, it's coming toward us. So this active region and that active region are the same one, just seen from opposite sides. Okay. Now they've continued to drift around, so they're now actually past the halfway part. They're overlapping more on the far side of the sun, but we still, with SOHO and SDO, have a good view. So here's a coronal mass ejection seen from the sun. Now here's one coming toward us. This is the outer corona, and this is the same event, but from the inner corona. You can also see planets going by. There was a great one recently of a comet that actually fell into the sun, but you can see the energetic particles associated with that. So when the CME does finally hit the Earth, it can cause a geomagnetic storm, but it is modulated. It's not just this mass of particles, the density and the velocity is important. But what's also important is the direction of the magnetic field in the solar system. The Earth's magnetic field, as you know, points north if you're near the surface, and it also points north. The boundary looks sort of like a dipole, where these boundaries are north. Okay, it points in the North Pole and out at the South Pole. At the place where the solar wind is coming, it's pointing north. And if the solar wind is coming with the north, which is with plasma that's also north, it just kind of bounces off and goes around. It compresses the Earth's magnetic field, like our force field and out there protecting us. If they're both northward, it pretty much just bounces off and goes around. If the magnetic field in the solar wind is southward, then it allows those two magnetic fields to reconnect with each other, annihilate each other, and allows the magnetic field from the sun to connect to the Earth, and that allows the energy transfer from the solar wind to the Earth, and then that gets stored in the magnetic tail, the aurora. The same magnetic reconnection process is what occurs on the sun as well for these flares. A magnetic reconnection takes these magnetic fields opposite senses, annihilating them and using that magnetic energy to accelerate particles. Here's sort of what it looks like in the Earth's vicinity. Two fields coming in, annihilating them and causing plasma to jet out the other side. We're now studying this process with multiple spacecraft missions. I've been working with cluster mission. We're getting ready to fly the MMS mission. And because this process, magnetic reconnection, is really critical in both stars, pulsars, and the sun, it's nice that we have, a captive model of it here on Earth that we can study. Well, solar storms have a tendency to be more likely when you have sunspots. And again, that's not surprising because of the same process the magnetic field affects it. Here's an interesting view of the velocity of the solar wind as seen by the ballistic mission. Actually went over the top pole of the sun not once but twice. And this shows you the velocity with 0% and 600 out here. If you look at the normal solar maximum, here's the velocity in green, high velocities at the pole, lower velocities at the equator, unless you're one of these strong holes and storms. The velocity is higher again. So the green is solar maximum. The blue is the solar minimum. Look how much slower the sun's solar wind is about a half of what's in solar minimum. Still higher at the poles, but much weaker at the equator. Well, the impact of this CME makes the magnetosphere shudder and brightens the aurora. It injects plasma deep into the magnetosphere. It can create a new Van Allen belt of energetic particles trapped in the Earth's magnetic field, and it can cause electrical current to flow in the ionosphere. We see these electrical currents by their perturbations of the magnetic field from the surface, and then one of those really strong electric fields occurs over a city, or in case of Canada, over a power line that went from a hydroelectric dam. Then that can cause a tremendous surge and cause a major blackout. This is the aurora from March of 1989. This is the one that caused the major blackout that caused the electric current associated with the aurora was right over the Great Lakes and right over this hydroelectric transmission line. This was the one that an aurora was actually seen in northern Houston during this particular event. And in fact, this little red spot over here in the Carolinas, I saw an email report from them. They thought it was the end of the world because the sky just turned blood red, and they had no idea what was happening. These are the power outages that occurred as a result of that March '89. The yellow is a complete power outage in Canada, but there was trips of equipment and damage of equipment all over. Even in parts of New Mexico had issues. The other thing that can happen is killer electrons. You inject these electrons deep into the magnetosphere, and the communication satellites that we have that do our cable TV, and in the case of Canada, also have all the banking done with satellite communication. So when the Anik satellites were zapped, the ATMs went down in Canada for 2 full days, and they figured there's $2 billion worth of business lost with not having any ATMs. Well, one of the things we're now doing is we're taking the solar wind velocity and direction of the magnetic field and creating what we call a flow index, which is an index of energy input. And then we've used that with the neural network to predict. We have 1 hour and 3 hours the KP index, the DST index, and the AE index, which are all auroral indexes, which is the total rainfall index, which is the total activity index. Now even up to 6 hours ahead. So this is an event that happened a couple months ago, but work that happened just last week. We did also extremely well. We send out red alerts when the energy input function goes really hot. And so anybody who wants to be on our alert, you can go to this website, mms.reiff.edu, and sign up for an alert. And we'll send out an alert at the energy forecast. We're now in the process of improving our forecast so they're regional. So we can say, okay, we think if you live in this region, that's where auroras are going to be, and that's our next project, assuming it's funded. Well, we're fortunate to live on a planet that's protected from the dangerous rays of the sun by our magnetic field, but there's another really important thing that our magnetic field does that really wasn't recognized until very recently, and that is it keeps our hydrogen from being swept away by the solar wind. As you know, helium balloons go up, and so does hydrogen. And the hydrogen and helium goes to our upper atmosphere where the ultraviolet light shines on us and ionizes it. If we didn't have a magnetic field, the solar wind would just sweep it away. And that's what has happened at both Mars and Venus. Mars has evidence that it used to have running water. Venus has evidence that it used to have water. We look at the hydrogen to deuterium ratio, we can tell that Venus used to have 10 meters equivalent of water. And where did that water go? It got lost in solar wind because they did not have a magnetic field. So when we look at what it takes for a planet to have life that continues, a magnetic field is critical. So Venus, we don't live there. Mars, we don't live there. So we're happy to be where we are. It is interesting that there are auroras on other planets. There are significant auroras on Jupiter, and the dot auroras is associated with the foot point of the moon Io that's blasting out all these particles into its magnetosphere. Saturn also now we now know has auroral, and again, part of those are associated with the moons, but less so because the moons are closer at Saturn. Even Mercury now, we know, has a small magnetic field. We've finally gone back to Mercury. We're finally seeing the backside of Mercury that we hadn't seen before. It does have a very weak magnetic field because it has a very large core, even though it spins very, very slowly. But as far as we know, it does not have an aurora. So we're very fortunate to have Earth as our spacecraft. Well, there's some great sources of space weather information. Spaceweather.com is a wonderful place to see auroras. We have our space weather alert system, and I'm going to show you a couple of things. This is the software that I just gave you. It's got a section. You install it on your hard drive, and then there's a section on the aurora, the Earth, the Sun, the planets in real time, and I'll show you how it works in just a minute. There is an Experience Aurora planetarium show that's going to be opening at the museum this summer, so you'll actually be able to see it. Now this is glad that happened. Now, I do want to show you just a brief a bit of the software that I just gave you, so you can see how you can use it. It's part of a larger piece of software called Space Update, which I do have a few of. We sell the full Space Update, but we give away the Space Weather. So if you go into Space Weather, you install it onto your hard drive. It's Mac or PC, except it doesn't run online. I apologize. And there are sections on the sun, the Earth, forecast missions, planets, and aurora. And the basics is where that the sun movie that I just showed you is in here. So one of the cool things about our software is you can pull. Nothing is hidden. You can go to the folders and pull out that movie and use it. Now, if I go to the sun in 3D, then I do have some interesting 3D images of the sun, and you need the red-green glasses to see them. But you can. This was when stereo was really new, and we're still relatively close to the Earth, so you could get a nice, truly stereo version. Now they're so far away, you can't really use the glasses to get that. In the section of the sun today, then you can see the images in various wavelengths of light. And I always like to sort of start with the visible part of the light. So here are the sunspots. And for each of these, you can click here. This was on the 24th, which is right about when the flare occurred. I go to the original site, it will bring down today's data, and it will replace that same image. So now this is the image of sunspots you'd see if you looked at today. And then you look at different wavelengths, you can see these other wavelengths. You can now see the convection at the surface. Again, I updated to today, and it will bring it down. And there's that sunspot again, and the light areas are called plages. Now, if you look in the magnetic field, what you see is each of these sunspots then is associated with strong magnetic fields. So the white is magnetic field out, and the black is magnetic field down. So when you see a white and a black right next to each other, that means it's a magnetic loop. Okay? So again, if I update this today, it'll be a lot less interesting because we just have that one sunspot, remember? So we only had one sunspot in the visible part of the spectrum. But if you now look at magnetic fields, you can see there's small-scale magnetic fields all over the sun. So all of these are great to look at. There's the inner corona. So this is the one that actually from just last week, the 21st of January, and so we'll there's a CME going off at the side, bang, and there you go. See the snow? Yeah. So that was the snow that came with the solar flare that caused all the excitement. The ones coming off the edge don't bother you, but the ones that are coming toward you, let's let it do that thing again. Boom. And if you see the Frosty the Snowman, then you know you're in trouble. Then I have the outer corona for the same event. Boom. So that was what caused all the trouble last week. But you can actually see the comets going into the sun. It's really quite amazing. So there's a lot of information about all the planets. There's images of the magnetic fields of the planets, and there's images like those movies that I showed you. One of the things that we do with space data is actually monitor the aurora from space, and we can watch what's happening. Okay, well anyway, that's in your present, and I do have some others. If you're a teacher, I have some things I'll give you. But we do have space updates for sale and DVDs of all of our classrooms. So we've got some great stuff that we've done with National. So I'm gonna throw questions. Yes. You.
Preparation for your lecture tonight.
Yes.
For the NASA Soho site.
Uh-huh.
And I ran across a really interesting discussion. We're talking about the difference between the solar cycle and the sun cycle. It says that the solar cycle, of course, is every 11 years. Mm-hmm. And so the sun cycle is every 22 years. And that's when the sun's magnetic field reverses.
Mm-hmm. Mm-hmm.
What causes it to reverse?
That's an interesting question. Okay. Now remember, let's think about our Earth. It's down at the North Pole and out at the South Pole, just like this. The Earth's magnetic field reverses also every 100,000 years or so. And in fact, we're heading toward reversal now. Less than 2,000 years, we will have a magnetic reversal. And things are going to be really interesting. We're going to not have a magnetic shield for some reason. We don't know whether it reverses by turning or just going away and coming back. And we're actually watching the magnetic pole move. Well, I'm just saying, yeah. I have it on another piece of software, but yeah, you can watch the magnetic pole move.
The magnetic pole is not aligned with the field.
That's right. It's offset by about 11 degrees. It's out of alignment. In fact, and that's another thing. On Earth, the tilt from the Earth's magnetic pole to spin axis is about 10 degrees. 10 or 11 degrees. Okay? It's Jupiter, 10 or 11 degrees. So it's it's always 10 or 11 degrees. Where's Saturn? It's completely perfectly aligned. Okay, well, so it's aligned to 10 or 11 degrees, and then we went to Earth with 67 degrees off. Okay, we don't know either. That's why I love this science, because take your best predictions and then you fall. Okay, back to them. So ultimately, this deep convection in the sun with a seed magnetic field that generates the large-scale magnetic field of the sun, and it's in one pole and out of the other pole. But over the course of time, those coronal holes start to approach the equator, and for the sun, it actually sort of flips. It almost flips over.
So coronal holes.
Those coronal holes match them up. You just have a coronal hole that stretches on this side, and stretches on that side of the equation. Oh yeah, we've seen it. But we haven't seen it happen on Earth, but we've seen it happen on the sun. Yeah.
Tom love children.
Oh, yeah.
Great. Two things. Didn't melt. So what about the heating rates? Like it still had volatile, so it still made it pale on the other side. What about drag? Eliminate the gas drag even at 100 kilometers from the surface. Why did it survive? And why did it suffer a lot of drag?
Well, it's a lot smaller than it was. It wasn't the same size coming out of the but okay, my model of the comet. I grew up in Oklahoma, and unlike people in the no snow at all, I don't want to get snow every day. You get 2 inches of snow, and you think, oh my God, I got to make a snowman. So you roll the snow, and every snowball has a layer of snow and a layer of grass. And a layer of snow and a layer of grass, and a layer of snow and a layer of grass. Guess what that grass does again? And in fact, those comets that nuclei that we look at have crusts that are insulated crusts. And if you look at the stuff coming out of comets, it's not coming out uniformly off the surface of the comet. It's coming out in these jets, these little holes. So I think it's that crust of grass, okay? We call it a dirty snowball. But I'll bet you what Lovejoy had was a fusion crust that helped protect it from the heat of the sun. You got a big enough mirror, you can stay cool from the sun. And it did, lost a lot, but it survived. Now there's another one that came in here, and it was glassy, and maybe completely, coincidentally, to the big coral mass ejection that came off the other side of the sun and that common area that I just said, wow, that is coincidence is something for that. And I can't believe it. There's a lot of things. We just find fun. Oh, yeah. Oh, yeah. Yes.
You say the magnetic field around your shield is from cosmic rays and charge solar wind. Reason field?
Okay. If the interplanetary magnetic field is northward, the Earth's magnetic field looks more or less like a dipole. It still has a magnetic tail. If you could see it, it would look like a comet. Okay? So it has a magnetic tail, but the plasma doesn't get in very easily because there's a northward magnetic field here, northward magnetic field there. It compresses it. So most of it goes around like a rock in a river. Okay. But if the magnetic field of the solar wind is southward, what you get is a reconnection of this exterior magnetic field with the magnetic field of the sun, and you now get open field lines that get stretched back. And now these allow free entry of anything, solar particles, cosmic rays. Okay, so generally the energetic particles from that flare have already gone past, but now the second flare occurs when the magnetosphere is open. Then you get a lot more energetic particles that can reach the Earth. Now they reach mostly at poles. So us folks that are sitting down here in 30 North, we don't care. We're protected by our atmosphere anyway. Okay, but it's only the people that are in a high-altitude aircraft or in the space station that go into these open field line regions are the ones that are most at risk from energetic particles.
And the picture you show with the sun flare and all of a sudden noise, that is part of it.
Those are energetic particles coming from the sun, and they if it's open, some of them will get in at the poles, but if it's closed, they'll just go around. So most of the time we don't worry about them. On the other hand, we had a really big solar flare. In fact, my very first publication was a giant solar flare on August of 1972, right in the middle of Apollo. And I had an experiment on the moon at the time. And I looked at the counting lakes, and it was just coming straight through my detector. We had a little aperture, counting electrons, and it was just coming straight. So we calculated it had to be at least 35 million particles. And we knew how thick our detector was. So we could figure out, penetrating radiation. If we had had an astronaut on the moon at this time, and that's true either on the limb or in the landmark, because they had no protection coming on this. One of the things that we worried about when we try to work with JCR is radiation prediction, so that we can try to see between how open the magnetosphere is and how much radiation is floating out there, and how much radiation we expect. One of the nice things about solar radiation, even these solar energetic particles, they're only 35 to 100 MeV particles. That's a lot of energy, but you can shield it with a couple of 3 inches of water. You can shield it. So in fact, if you built your space capsule and you stored all your water, in a double tin, you'd be relatively protected, and you can make a hiding hole. Because the sun, pretty much it's only 8 minutes. Well, you don't, because when you see it, it's there. It's traveling at the same speed of light that the light from the flare does. But they last, it's usually like this laser flare lasted almost a day. Usually they don't last but about a few hours. But you can go into your hidey hole and protect yourself from the solar stuff. In fact, it's the galactic stuff that's the hardest to shield. Because now this is GE particles. And there's no shielding that can shield you from GE particles except like 10 meters of lunar level. Okay? So, in fact, it's safer to have a manned mission of solar maximum than a solar minimum. Because you can shield the solar particles, but you can't shield the galactic particles. And the sun's maximum without the galactic particles. And it's a factor of 34. So that's the other thing to worry about is the galactic particles. And in fact, sun shield is actually worse than underwater because you get energetic particles hit the side of your spacecraft and now create a shower. Less energetic, so it's exactly the same. So they're not very many of them, but they're constant. Yeah. You don't want, as I said, the negative aurora sort of tells you where the open close boundary is. So if you cross over the aurora, that's when you are in the open field. If there's nothing happening, then it's not. Yeah. Okay. But they're not protected by the atmosphere at that point, and they're not protected by the field at that point. So it's not really part of when that happens when they're over the aurora. And in these big events, the aurora goes equator. So, these big events really let us know what's going on. That's the problem. I have friends that model based on the sun, look at magnetic fields of the sun, and they have a Slumbering model, and they can say, oh, it's going to be streamed, it's going to rise within a couple of hours, and it's going to have this much velocity, but they still can't predict whether those directions. So what we do is we measure it at the 8 spacecraft, which is now 45 minutes. That's not a whole lot, but it's better than nothing. Okay? So we get the 45-minute propagation time, and there's about a 45-minute storage time. And that's why we can do a really good 1-hour prediction, a pretty good 3-hour prediction, because of the continuing energy input. It goes longer. Let me show you one picture of this. Now this is my real time forecast model. Okay, this is from this event that we just talked about. So here's the energy, and so this is actually measured in kilovolts. The average forecast is about 47. Here's the energy input. And it's bang up over 250. Relatively short lived, and so here, and then another big one, and this is the second split that came on later. And here are our predictions of the activity. So we predicted strong activity. The red is what was actually measured, estimated. So the red was measured. Blue is what we predicted. And the one thing the one we missed is this one right here. That's on. I'll do it here. See these red dots right here? That's a miss. We missed that. And why did we miss that? Because that was a case where the energy input was modest, it was not small, but there was one of these solar energetic particles at the same time. And that changed the conductivity on one. So this extra activity right there was caused by one of these 1-2 particles, the second flare that occurred while we were still recovering from the first. Other than that, that's and there was a big storm, but it was the only really miss we've had in the 8 years that we've been doing this prediction. But again, that just says, hey, there's a lot of stuff we don't know yet. But we're doing quite well. I'm quite proud of it. Yeah.
said something about I really told
So, it's in band. Yeah. It turns out there is a north-south asymmetry because the north has more of the land. And it didn't get installed at the equator. So the solar activity temperature changes are more regional rather than global. But the clouds happen more near the poles because that's where the particles get in. So it's really a relatively high latitude cold. And the opposite thing was, when the Vikings were here and the temperatures were so warm, that again was more regional.
By the way, inside.
Oh, yeah. Yeah. If you can see them in water bags, you still have fun. Yeah.
Similar to earthquakes and volcanoes, the longer the going period, the greater the series of violent. Is that also?
No, not really. It's just like the Earth's magnetic field really doesn't have a memory of much more than a day. When the input stops, it will all settle down. And now the sun's active regions will last for a few months. So if you've got a set of aurora at a certain time this month, like 21st, 24th, 25th, if you want to go take a trip to Alaska, I would go 27 days after this. And you might really get the good work. So there is this 27 days that it's tested for as that same active region comes back around. But again, the storage is relatively temporary. So you don't build up for years and years like you do on a earthquake. Earthquakes can build up strain over decades. Here, it really is more how much energy is released in that particular event. Because realistically, you can't build up too much because of the release process.
Yes, it has spectacular videos. But the mass projection, all kind of off the room, people off and come to gas. A lot of it goes falling back and gets the wood.
It's pretty bright, yeah. Well, again, that just material hitting the surface and got energy and involved.
Just the velocity.
Yeah. That's a lot of mass. Other thing that was really, really interesting, they showed, I used to show them this, there was a coronal mass ejection that passed the comet, and the magnetic field of the coronal mass ejection interacted with the magnetic field of the comet and split the comet field. That was oh man, that was so cool.
That was, I read about this people. They said the scientists now can actually detect sunspots forming 12 kilometers below the surface in a certain amount of time. They said that sunspot would form if we migrate to the surface. So they get the warning now ahead of time. That's their current surface.
The other thing that's really cool that we're now doing is called solar seismology. And they can see the sun's mode of flexing and can tell that there's a sunspot on the backside of the sun by the wave structure of flexing. But realistically, once you got a sunspot, it's still sunspot. You have to go from the sunspot to really increasing that magnetic field near the sunspot. So, the real.
I was wondering how you're not observing the surface. How can you tell a sunspot is forming 12 kilometers below the surface?
Again, it's the solar seismology.
Oh, okay.
It's, yeah, the surface place. And in fact, one of the things that we've seen now, there was a solar flare, and you could actually see the blade propagate on the surface of the sun of the solar flare. Now that we've gotten better and better instrumentation, we can see things that do that. It's still a lot. Yeah.
Yeah, the wobble effect on the sun from that. How does that impact this?
But that's really more of a full thing. The flares are really more, much more of a small scale lining up of things. The Jupiter effect is really a full gravitational pull. Now, can gravitational pull do things? Sure. I mean, that's why Io has volcano. Is because its orbital period is 1.75 days, and the next one is exactly double, and the next one is exactly double, so you have this resonance. So every time Ganymede and Callisto goes by, they pump Io because it has volcanoes. That was probably the best timing of any science paper I've ever seen, is that they predicted volcanoes would high up in weeks before they would. Usually you predict it either way too far in advance and nobody remembers, or exactly the No, not a prediction, as W. Barrow says, but one of the things that we would like to do, if I were to say, how would I improve our maybe the monitor that we need. The first place we need to replace A is on a flat leg. It may not make it. It's longer. There is a spacecraft that they're talking about wanting to be able to monitor and function. But ultimately, what would be really cool is to get a solar sail. And with a solar sail, you can negate part of the sun's gravitational pull. And so, right now, the A spacecraft is at the Lagrangian point, which is the balance of gravity between Earth and the Sun, and it's about 200 Earth radio upstream in about 45 minutes. But if you could then kill off more of the Sun's gravity using the solar sail, you could now have your Lagrangian point much farther out. And if we could get 3 or 4 hours of one instead of 45 minutes, then you could really do some good with the astronauts, could really change aircraft routes and have some confidence. Because you don't want to fly wolf and get everybody excited. That's all. Okay, I think I will quit, but I do have some others too, so let me go. There you go. You warned me, so that's why I brought this up.